Welcome to ASU's University Academic Success Programs. This video will cover the topic, Electron Configuration.
What do we use electron configurations for?
Electron configurations allow us to express how electrons are distributed within an atom by describing them in atomic or molecular orbitals. The periodic table is organized in a way that allows us to conveniently identify the electron configuration of different atoms. The numbers correspond to the electron shells, and different shells can hold different numbers of electrons. For example, shell 1 can hold 2 electrons, shell 2 can hold 8 electrons, and shell 3 can hold 18 electrons. The letters S, P, D, and F correspond to atomic subshells or orbitals within the shells, and different subshells can also hold different numbers of electrons. For example, the S subshell can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and the F subshell can hold 14 electrons. Looking at an energy diagram, we see that the energy of electrons increases as the shell number increases, and there are different energies associated with the different orbitals as well. The rules for filling S and P orbitals remain fairly straightforward, while D and F orbitals become a bit more complicated. In general, electrons will occupy the lowest energy orbital possible. Looking at the diagram, this means that orbitals will fill from the bottom up.
So how do we actually determine the electron configuration of an atom?
Let's take a look at carbon. Neutral carbon has 6 electrons. Each square in the energy diagram can hold 2 electrons. One electron will be drawn as an up arrow and one as a down arrow. These arrows correspond to the spin of the electrons. Since carbon has 6 electrons, we start by drawing arrows in the 1s orbital and filling squares until we have drawn 6 arrows total. We see that the electrons fill the 1s atomic orbital, the 2s atomic orbital, and occupy part of the p atomic orbital. We therefore write carbon's electron configuration as 1s2, 2s2, 2p2. The superscript on each letter corresponds to the number of electrons in the orbital.
So, we write out all the orbitals that electrons are present in?
That's one way to write electron configuration. Another way is to write the configuration relative to the noble gases. When there are many electrons in an atom, it can be rather long to write out every single orbital. Instead, we can write out only the orbitals that contain valence electrons and represent the core electrons as the noble gas of the preceding period. In this example, carbon has 4 valence electrons and 2 core electrons. The core electrons can be represented by the chemical symbol for helium because helium's electron configuration is 1s2. So instead of writing 1s2, 2s2, 2p2, we can write in brackets He, 2s2, 2p2.
Okay, so in this case, two notations are approximately the same length. What if we look at an atom that has more electrons?
Good idea. Let's take a look at potassium. Neutral potassium has 19 electrons, so we need to fill our energy diagram with 19 arrows. This fills the 1s, 2s, 2p, 3s, 3p, and half of the 4s orbital. Potassium has 1 valence electron, and the core electrons can be represented by the chemical symbol for argon, which is the preceding noble gas on the periodic table. This notation using the noble gas conveniently shortens the electron configuration for potassium.
Okay, so when we write electron configurations, we are expressing how electrons are distributed within an atom by describing them in orbitals. The letters correspond to orbitals, and the numbers in front of the letters correspond to the electron shell that orbital is in. The superscripts on the letters refer to how many electrons are in the orbital. To shorten electron configuration notation, we can represent the core electrons as chemical symbol of the corresponding noble gas.
That's exactly right. Great work!